let's move to the next one, which is already on the display. I'm very happy to introduce Sebastiano Pilati from University of Camerino. Welcome, thank you for accepting the invitation. And he's going to talk about accelerating spin glass simulations using quantum annealers through deep learning. The floor is yours.
Okay, thank you very much. I think you can see my screen.
Yes, we do. Now we see the slideshow.
Okay, now it's full screen. Let me also take a laser pointer. Okay. No, I don't have it. Yeah, here it is. Okay, so let me start by thanking the organizers for organizing this very interesting workshop and also for giving me the opportunity to give this presentation. So as you see from the title, I will discuss the problem of simulating spin glasses, and what I will try to show you is how you can use quantum annealers combined with deep learning techniques to accelerate and speed up the simulation of spin glasses at low temperature. That is a challenging computational problem. And let me also mention the collaborators. So here in the bottom left of the slide, you see the people that have been involved in the research that I'm going to describe. In particular, I would like to mention Giuseppe Scriva, who's a graduate student here at the University of Camerino, and also Benjamin McNaughton, who has shared the PhD position at the University of Camerino and University of Antwerp. And these two guys did the hard part of the work that I'm going to discuss. So I don't think I have to spend much time with this audience to describe the problem of spin glasses, but I will say a few words that are useful for me to introduce the problems that I have in mind. So here we have in mind a classical spin glass Hamiltonian, where we have binary variables xi or xj. We can consider binary values plus and minus 1, and these variables are coupled by, let's say, random couplings jij. Okay. Now it is known that these systems, these Hamiltonians, display glassy phases at low temperatures, depending on the type of graph your spins are attached to. For example, if you just have a 2D square lattice, you actually have a spin glass phase only at 0 temperature. But in general, if you have a higher connectivity or higher dimensional system, you have a finite temperature phase transition to a spin glass phase. And in fact, many people in this audience are probably also interested in the problem of finding the lowest energy configuration, okay, that is related to Kubo problems, to quadratic unconstrained binary optimization problems. And in general, at least if you are not on a panel graph, this is NP-complete problems. And also computing the partition function on a non-panel graph is an NP-hard problem. So it is in general, it is known that simulating spin glasses at low temperature and simulating their thermodynamic equilibrium is a challenging computational task. And here on the right, you have a plot of the autocorrelation function, of the energy autocorrelation function that you would obtain if you use the standard Metropolis algorithm to simulate the thermodynamic equilibrium properties at different temperatures. And notice the the semi-log scale. So at high temperature, when the inverse temperature beta is small, your standard single spin flip Metropolis algorithm gives you a very efficient simulation. But if you decrease the temperature, at some point you see a freezing, and at some point the simulation is pathologically inefficient. Now, of course, there are more efficient computational algorithms. They do exist already. One can mention parallel tempering or the isoenergetic cluster updates developed by Camerino and collaborators. But it's fair to say there is no one-fit-all solution that can easily simulate spin glasses on arbitrary graphs. So here what we want to discuss is how we can use adiabatic quantum computers or quantum annealers like the ones that can be provided by D-Wave in combination with classical deep learning techniques to accelerate the simulation of these systems at low temperature. Okay, so here you see that we have in mind a hybrid approach where we combine quantum annealers with, let's say, we can say high performance classical computing in the form of classical deep learning. Okay, and so we will use deep neural networks. Now, we will use specific types of deep neural networks that belong to the category of generative neural networks. These are models that are usually used via what you will call unsupervised learning. So you have unlabeled data, and you imagine that these data have been sampled from an unknown probability distribution, and then you are trying to infer this unknown probability distribution from sample data. And typically you train them by maximizing the data log likelihood, which is equivalent, as we will see later, to minimize Kullback-Leibler divergence from your model to the unknown distribution. And here you see an example taken from the literature where generative neural networks are being used to create realistic images of human faces. Okay, they are, once you have trained your model, you can generate images that look very realistic, even though they are different compared to the ones that were in the training set. Okay, and now a problem that is relevant for us and will be useful is to see whether a generative neural network can learn to accurately approximate the Boltzmann distribution of a spin glass. Okay, now we know that in general with spin glasses and with many disorder models, we have really rough energy landscapes, like here we have a cartoon like the one represented by this black curve. And the Boltzmann distribution at high temperatures, which is represented here by the red color, will be kind of broadly distributed. But if you decrease the temperature, you will have peaks in the minima. Of course, an important problem is to make an ergodic simulation which explores the full configuration space and especially touches all of the relevant minima. In particular, the deepest minimum is the one that is more interesting. And what we would like to have is that a model is that approximates the Boltzmann distribution, in particular at low temperature. For example, you might want to have a curve like the green one. Okay, and the problem here is to understand whether a generative neural network can approximate it, but also whether we really need to approximate it accurately, or maybe even an approximate model is good enough for us, and we will see how. So now we further specialize. So we will take a specific kind of generative neural networks that goes under the category of autoregressive neural network. So what we obtain with such an autoregressive model is that the probability distribution corresponding to your model is actually written as a product of chain conditional distributions, where the conditional probability distribution of the spin D depends only on the previous spins that you have seen in a specific order that you have to choose. Okay. Now, why do we want to have such a property? Well, we get two important features that are very important for Monte Carlo simulations. First, you can get direct samples from this from the unknown distribution, from the model distribution, via so-called ancestral sampling. Okay, so you sample directly the spin D given the previous ones, and you also have a directly normalized probability distribution. Okay, so it's like to say that the partition function is known and it's equal to 1. Okay. And here you have on the bottom left an example of an autoregressive model. This is, let's say, maybe the simplest one. It's called neural autoregressive distribution estimator. And you see the type of structure that of this neural network that gives you this autoregressive property. And there are also different type of models, more advanced, and we also use them, and they give somewhat improved performance, but more or less these different type of autoregressive models share the same type of features. Now, why do we want to have these kind of models? Well, because we can implement what we call neural Monte Carlo simulation. Okay, we can use a generalized metropolis hosting algorithm where the proposal distributions are directly generated by the generative neural network. Okay, and you just have to generalize your acceptance probability, and you might get an efficient simulation with fantastic Monte Carlo updates that allow you to jump from one configuration to a completely different one. Okay. Now, the only requirement that you have is that whenever the Boltzmann distribution is not 0, then also your model distribution should be larger than 0. Okay, this is the mathematical condition that has to be fulfilled, and we will discuss it later. And what we want, hopefully, is that the model distribution approximates accurately the Boltzmann distribution, because in that case, your acceptance rate is close to 1, and so you get a fantastic simulation which explores the configuration space efficiently and with very high acceptance rate. Okay, and here you see a list of related works that have been published also recently, and they performed a similar type of research. I might mention these last 4 papers and point them out, just to mention that in this case they use a different type of generative neural networks called normalizing flows that also allow you to perform direct sampling, and they give you normalized probability distribution using a different strategy compared to the autoregressive models. And they have been used mostly for continuous variable problems, in particular for molecular simulations. Now, there are 2 types of training strategies to train such a network. Okay. Now, one that might appear particularly appealing is to minimize what you would call the reverse Kullback-Leibler divergence. Okay. Now, you might be aware that the Kullback-Leibler divergence is a measure of difference of distance between 2 probability distributions, but it's not symmetric. Okay. Now, to minimize the reverse Kullback-Leibler divergence, you will try to minimize this quantity here. In particular, the second expectation value is the one that is relevant. And the particular appealing feature here is that, in fact, to compute this expectation value, you don't need data. You can just sample the data from your neural network, because you get an expectation value on the probability distribution corresponds to the model, which means that you can train the network on data generated by itself. So essentially, you're using a reinforcement learning approach, which looks like a promising feature. But it has already pointed out in the literature is that this type of training is particularly susceptible to localization in metastable states. In particular, when you want to discover and learn a multimodal probability distribution, which is the typical case that you encounter in spin glasses. Okay, so here we use a different approach, which is the one to minimize the forward Kullback-Leibler divergence. Now, I will show you that this works well, but it has a drawback, is that you need to minimize this quantity, and you have an expectation value over the Boltzmann distribution. And of course, we don't have a priori data generated and sampled from the Boltzmann distribution. That is the original problem that we want to solve. Okay, so here the problem is that we need data for training. Okay, and here we will discuss 2 strategies that can be used to solve the problem. One which is purely classical, and we implemented recently, and we called it sequential tempering. And the second one, which is probably more interesting for this audience, is to use data from a quantum computer, an adiabatic quantum computer, so from the wave, essentially. Now, what would you do with this neural sequential tempering that I'm mentioning? So essentially, the idea is to start performing your simulation at high temperatures, where even a conventional single spin flip Monte Carlo simulation would work easily. You produce data, you save them, you train a neural network, and then you use this neural network at a slightly lower temperature, and then you run a neural Monte Carlo simulation driven by a neural network. You save more data, you train a new network, and you proceed. Okay, and what we have seen is that you can reach the low temperature regime and perform efficient simulations of spin glasses at low temperature. Okay. Now, this sounds good, but you see the problem is that the protocol is long. It is computationally expensive, okay, because you have to perform many simulations starting from high temperature and train several neural networks. Okay, so our goal here is to use a quantum annealer to jump directly to the low temperature regime, which is the one which is interesting for physics and also for optimization problem. It is the one which is challenging for computational simulations. So let me show some data first, working on synthetic data, so data generated by a classical Monte Carlo simulation. And here, these examples are shown for a relatively small system, just a 2D lattice with 100 spins. And you see the average energy that you obtain as a function of the depth of your neural network, in particular the number of hidden neurons that you have in the hidden layer of a neural regressive distribution estimator. And you see that even the energy that you obtain by doing an expectation value over the model distribution in black converges to the exact result, which means that the neural network is learning to approximate the Boltzmann distribution more and more accurately. But more importantly, the expectation value over the neural Monte Carlo simulation is always unbiased. Okay, so you don't need to exactly approximate the Boltzmann distribution. The Monte Carlo simulation is always exact. It might be more or less efficient, so you might get larger or smaller statistical error bars, but in principle, your result is unbiased. And here on the right, you see that indeed the acceptance rate increases when your neural network becomes deeper, and so it can approximate the Boltzmann distribution more accurately, and so you get a more efficient simulation. Now, here is the interesting part, because here we work on data generated from the quantum annealer. And here on the left, you see some histograms of the energy distribution that you obtain from samples from the wave quantum annealer. Here, the data are actually from the relatively old device, the 2000Q device. We are working on advanced, and we obtain access to it via Cineca, via NISCRA Class C project, and we're very grateful for that. And so you see the three data sets corresponds to different annealing times. As we expect, for the longer annealing time, that here is 100 microseconds, the energy distribution has more weight on low energy configurations, and here actually we sample frequently also the ground state. Okay. What is interesting to see is that when you train your neural network on such data and you perform a Monte Carlo simulation, you get an exact Boltzmann distribution. So here you see in blue the original distribution of the data from the quantum annealer. Okay. With the gray color, what we obtain with our computationally expensive sequential tempering procedure at low temperature. Here beta is equal to 2.2, so you are almost you're very close to the ground state energy. And you see that the data from the neural Monte Carlo simulations are unbiased. Okay, so this shows you that the neural network is ergodic enough, let me say, put it this way, to propose updates that explore the full configuration space. And what is interesting to notice is that the acceptance rate becomes higher, in particular at low temperature, so for large beta, okay, if your neural network has been trained on the wave data obtained with a longer annealing time, okay, because that's where you expect to explore more frequently the low energy part of the configuration space.
Sebastiano, you have 1 minute left.
Okay, I'm finishing up. This is my last slide, actually. So here in the top left, you see an example of a Monte Carlo simulation at a low temperature. So in blue is the trivial single spin flip algorithm. You see that it converges to the equilibrium energy in a huge number of Monte Carlo steps, while the neural Monte Carlo simulation driven by network trained on D-wave data converges almost immediately. And what is interesting is this plot in the middle, where we have the energy as a function of inverse temperature, and in red you have the exact results that we obtain with this sequential tempering. And with the different colors, you see different types of neural Monte Carlo simulation where the neural network was trained on D-wave data. And you see that in interesting regime, the low temperature regime, which is on the right, we get unbiased results. Of course, we see some problem at high temperature on the left because the D-wave data do not span the high energy sector. But this is a problem that we can easily fix by using a hybrid approach where we combine the quantum data obtained from the quantum annealer and classical data obtained with a classical Monte Carlo simulation performed at high temperature. And when we train the neural network on the hybrid data set, This allows to perform an efficient simulation with the black color, which is unbiased at all temperature, both low and high. So this hybrid approach, where we combine the quantum data from the D-Wave and the classical Monte Carlo simulation for high temperatures, allows to perform an efficient neural Monte Carlo simulation at any temperature. Okay. This is my last comment, since I have run out of time, and so I stop here, and I thank you very much for your attention.
Thank you so much. Indeed, we run out of time. We have no time for questions, but let me ask a very quick question to you, which is about quantum advantage. Do you see here the chance to having advantage at some point? Can you say just a sentence about where do you see the threshold?
Yes, I mean, we clearly see that it's easy to accelerate the Monte Carlo simulations. It is not easy to be quantitative on the concept of advantage because we don't know exactly what to compare to. Probably we should compare to parallel tempering, but at the moment we didn't make a one-to-one comparison in terms of computational time, because also parallel tempering will be computationally expensive, and so we don't know exactly how much time it will take to perform the type of simulations that we are running at the moment.
Okay, thank you so much. Thank you for this excellent talk. There is a question in the chat, so maybe you can answer typing in the chat.